Hi, everyone. So recently, we have been talking about electromagnetic energy and how electromagnetic energy has different wavelengths of light. Because of the different wavelengths of light, their frequency is different and the energy. Now, with stars, this is really important information because it tells us about what it's made of, how old it is, and really the elements that are going to be produced along the way. So, refresher before we start, let's think about fusion. We know it's one of the most powerful things that occur. Quick video. That's the core. So in the video, they did talk about how two atoms of hydrogen come together, but that's deuterium and it's a little more complicated. So for us, we've been talking about how four atoms come together. So again, in the video, it said nuclear fusion occurs within the core, the center, due to intense heat and intense pressure. They said gravity is crushing so much together that it's a very high pressure and therefore a very high temperature. And within the fusion reaction that we've been talking about, four hydrogen atoms combine to form one helium atom. And during the reaction, mass is lost a little bit, and it's not necessarily lost, but it's converted or changed into light and heat energy. So we know a lot more about light now. We know the different wavelengths, we know how it has different energies, and we also know how to determine what stars are made of. This is a really, really important idea when it comes part of fusion. Over time, the new elements that are made, like helium, will combine to form other heavier elements. So within this diagram, we can see that if we take two helium atoms and combine them, they would form a beryllium atom because the number of protons is different. If we take a beryllium atom and combine it with another helium, this will make a heavier element, carbon. Again, protons are coming together, so we are making new elements. And this reaction just continues on. So the total amount of energy that a star puts out as light each second is called its luminosity. Recall on our little star cards, we were looking at luminosity relative to the sun. So if it has a luminosity that's greater than 1, a star is putting out more energy every second than our sun. If the star has a luminosity less than 1, that star puts out less energy than our sun every second. So luminosity, how much energy is being released every second. And because the amount of energy is different, it's related to the color. So once we know how much energy is being put out, we can determine the color generally. And color and surface temperature are directly related. We saw that when we graphed our stars. We saw that bluer stars are hotter compared to red stars, which are less hot. Remember, stars aren't cool. They're still really hot. So the way that we are able to determine the temperature and color of a star is by looking at the wavelength that a star emits the most light. And we call that the peak wavelength. So notice we have wavelength here on the bottom of our graph. The 300 wavelength means it's small, it's close together. Where 800 wavelength, they're very far apart, so they're going to have less energy. Wherever we have that peak, that spike, that is the greatest amount of energy at that wavelength that's being produced. For here, we can look at emission spectra. We looked at that quite a bit at the top. Notice how some lines are brighter than others. The brighter the line on the emission spectra is related to the intensity, how much of that wavelength is being released every second. Because remember, the orbitals are different distances, so electrons are moving different amounts, which is going to release different amounts of energy. So how are color and temperature related? Well, if the peak wavelength has a shorter wavelength, so the number's smaller, they're closer together, we know that a short wavelength closer together is more energy. Those higher energy waves are going to cause stars to be blue in color, and they are going to have a higher temperature. We saw this on our graph, that those blue stars had, in general, a higher luminosity and a really high temperature. That's because they release the greatest amount of energy that they're releasing is at a shorter wavelength. So blue are hot, higher temperature, overall a shorter wavelength that is being released. Where then we have the opposite. So if the peak wavelength has a longer wavelength, meaning they are farther apart, they have a bigger number, we know that's less energy that's being transferred. Less energy is going to cause a star to be red in color. We know that based on our visible spectrum as well. Red has a longer wavelength than blue. So less energy, redder in color, and it will be a lower temperature relative to blue stars. This data table right here tells us the relationship between the temperature of a star, its color, and also the peak wavelength. This data table will always be given to you. You do not need to memorize it. We just need to know how to use it. So let's have a little practice with it. Oh, fun fact, purple and green stars do exist. They're just a mixture of the higher wavelengths. Our eyes don't interpret it that way, so they look white to us. Yay. Okay, so let's have an example. The star to the right emits a peak wavelength of 415. That's this highest line, or highest intensity. It's 415 nanometers. What can we conclude about the color of a star? Using our data table, we see the key information is 415 nanometers. On our data table, we want to find where that wavelength falls within the range. And we know that 415 falls between 380 and 450. So we're going to be using this row of our data table to answer the question. So number 1 says, what can you conclude about the color? We can conclude that it is blue because the peak wavelength is within this range and the color would be blue. Number 2, according to this data, what's the approximate temperature range? Include units. Again, same row in our data table. We can find that the temperature range is 28,000 Kelvin, that's the K, to 50,000 Kelvin, K. We looked at that unit when we were doing our star cards as well. So just by knowing the peak wavelength, we look for the range, we can determine the color and the temperature. If I tell you a star that has a surface temperature of 9,000 Kelvin, we can look where 9,000 Kelvin falls within our range. We can see that it would be blue light, and this would be the possible peak wavelength. So as long as we're given one piece of information, we can determine what the other pieces of data will be about the star. All right, about 20 minutes into class, the check-in for energy production of stars will be posted, so keep an eye out for that. Bye, friends.